Heat transfer, specific heat, and calorimetry. This is the big part of the chapter, the calorimetry. So we're going to spend some time on that. Now, energy transfer. When two objects are at a different temperature and they're placed in thermal contact, we can transfer some of the energy from one to the other. Okay, the temperature of the warmer object will decrease, the temperature of the colder object will increase, and the exchange of energy is known as heat. They will continue to exchange heat until they reach thermal equilibrium. Right? Now, heat compared to internal energy. As I said before, we have a slightly different definition for heat than what we think of in the popular world. In physics, again, heat has a very definite definition, okay? It is the thermal energy going from one object to another, one system or another. Internal energy is all the energy already in the system or object. So if heat flows from one object to another, it is the internal energy that is going to be affected of the object which is receiving the heat. Okay? So heat, thermal energy in motion, internal energy, a thermal energy that has arrived or is leaving. Okay? Now, what is internal energy? Internal energy, well, we oftentimes use the symbol U for internal energy, and that's sort of unfortunate because that actually can also mean potential energy. But internal energy is all the microscopic components of energy of that system, okay? It could be kinetic energy, these molecules moving around. It could be the potential energy due to the intermolecular forces. It involves everything. The kinetic energy from translation, the kinetic energy from rotation, the kinetic energy from vibrations. It can be the potential energy of the van der Waals forces between molecules. It can be the potential energy of the electrons in their orbit around the atoms. It's just a summation of all the energy that's there. Okay? And as we heat or cool an object, we change the internal energy. If the temperature goes up, it's the kinetic energy that's increasing. If the temperature goes down, it's the average kinetic energy, again, that's decreasing. But we can exchange heat, we'll talk about this in the next section, without changing the temperature, where a phase change takes place. And that's where we're affecting the potential energy. So again, internal energy is just basically a summation of all the energy that we don't physically see, but microscopically it's there. All right, again, translational energy. What do we mean by that? Well, all molecules are moving around, right? They all have mass. They have different velocities. Okay, so we're talking about kinetic energy here. Now, what's interesting is if we compare a cold gas to a hot gas, on this axis, we have the number of molecules. On this axis, we have the speed of the molecules. So that's sort of related to the kinetic energy. Now think about this, okay? When the gas is cold, all the molecules are pretty much moving at a slow velocity. So we have a low kinetic energy. As we heat it up and the temperature becomes greater and greater, this peak shifts to the right. The velocity is increasing, so the kinetic energy of everything is also increasing. Okay? But that's not the only type of kinetic energy we can have. All right? Not only the molecules moving around in all different directions, they also can be vibrating, where this vibrational energy, okay, is basically connected to what we said with the energy of a simple harmonic oscillator. Now, this is a CO2 molecule, okay? Look at it. One mode of vibration has the oxygen moving up and down with respect to the carbon, in and out with respect to the carbon, and even the carbon can move with respect to those two. It has 3 different modes of vibration, right? In fact, these different modes of vibration are one of the reasons why it's such a strong absorber of infrared light. The vibrational energies are right around the same frequency as infrared light, so these molecules will very easily absorb the infrared light. Rotational energy. Not only can molecules translate, move around, not only can they vibrate, but they also can rotate. And in physics 1, we found out that the kinetic rotational energy is equal to 1/2 I omega squared. In fact, when you use a microwave oven, what you're doing is you're tuning the microwaves, which are electromagnetic waves, to the rotational energies of the water molecules. Because water is polar, this oscillating wave comes in and creates a torque on the water molecule, where the water molecule is always trying to realign with the electric field, but because the electric field is changing, it causes them to spin faster and faster and faster. So right there, you can see 3 different forms of kinetic energy that add to the total internal energy of molecules. All right, let's talk about the potential energy. Van der Waals forces. The intermolecular forces generally come in, I don't know, two flavors. You have, actually 3. You've got hydrogen bonding, which is the most extreme of the dipole-dipole intermolecular forces. You have London dispersion forces, which are temporary dipoles. But in any case, it takes a large amount of energy these are hydrogen bonds right here between 2 water molecules, but it can take a large amount of energy to separate the molecules due to these intermolecular forces. Okay? If we add heat to the system, we can break these bonds and go from a solid, like ice, to a liquid, water, to a gas, steam. And of course, covalent metallic and ionic bonds have even stronger bonds between them, okay? This leads to even more potential energy, okay? So as we heat stuff up again, this can lead to a phase change. Okay, there's even energy associated with removing electrons called ionization energy. Okay, so what is this internal energy? Well, the internal energy is basically everything. It's kinetic energy, it's potential energy, it's all this microscopic stuff going on that we don't actually see from the outside. Okay? Yeah, we can view a phase change, but we don't actually see the molecules moving around in terms of their kinetic energy or breaking bonds in terms of their potential energy. So when talking about how a system works as we add heat, we generally say heat, which we use a symbol, we use a symbol Q for, okay? If the heat is positive, the heat is going into the system. If the heat is negative, then we're extracting energy from the system. In any case, if no work is being done by the system, don't worry about this. We're going to talk about work later on. If no work is being done, The change in internal energy of any system is equal to the heat being added, okay? Sorry, didn't mean to put that. Won't erase, there we go. The heat being added by this to the system, okay? Q represents the heat going into the system, okay? Conservation of energy. If you're gaining internal energy, it's got to be coming from someplace. It's coming from heat. If you're losing internal energy, then you're giving heat up. Okay, units of heat. Well, the SI units of heat, of course, since heat is energy, the SI units have to be joules, okay? But there are other units in the metric system that we also recognize. A non-SI unit is the calorie. Calorie is based on 1 gram of water going from 14.5 degrees Celsius to 15.5 degrees Celsius. I have no idea how they came up with those temperatures because the heat capacity of water does change a little bit with changing temperature. But basically, the calorie tells you how much energy is necessary to change the temperature of water per unit mass, okay? Basically, the calorie says 1 calorie equals the amount of energy we need, okay, to change 1 gram of water, increase it by 1 degree Celsius. Okay. Now, converting calories to joules, it actually takes 4.186 joules to heat 1 gram of water by 1 degree Celsius. So that's how many joules there are per calorie. Okay. Usually we can just round it up to 4.2. That's good enough. So you have 20 calories. You want to convert that to joules, just multiply by 4.2. Okay. You get 84 calories. If you want to go from joules to calories, you got to divide by 4.2. There you have 12 calories. Oh, this annoys me. Food calories are not the same as metric calories, okay? Food calories are sometimes called big C calories as opposed to the metric calorie, which is a small C calorie. See, in this country, food calories are 1,000 times greater than the standard calorie. Outside the United States, we generally refer to the food calorie as a kcal or kilocalorie. So that eliminates the confusion that you might have between the big C and the little c. All right, let's take a look at this. Here we have a food label, and they tell you, oh, come on. 250 calories per serving. Okay? Well, those are food calories, folks. So if we take 250 food calories, that's 250,000 regular calories. We multiply it by 4.2, okay? That is over 1 megajoule or 1 million joules of energy, okay? You never realized that your food had that much energy. But yeah, 250 calories is basically 1 million joules of energy. And that helps power your body. Here we have an example. A student eats a breakfast consisting of 2 bowls of cereal with 320 calories of energy. Okay? Food calories. That's 3.2 times 10 to the 5th small c calories. He wishes to do an equivalent amount of work by curling a 25 kilogram barbell. How many times must he raise the weight to expend that much energy? Okay, so work is going to equal this times this. So you want 1.34 million joules of work to be done. that will be equal to 2n, positive rep, negative rep, n's a number of total reps, times the potential energy, okay? So n times mgh. We want to solve for the number of reps he's got to do, and he's going to be disappointed. 6.84 thousand reps he's got to do. I don't know if you've ever done arm curls before, but you're not doing 6,840 reps. I don't care how little weight is there. What he's missing here is the point that muscles are not 100% efficient. Your body has a very, very low efficiency. So to burn that off, most of what you're going to burn off is going to be lost in the form of heat, okay? So yeah, you won't have to do that many calories to burn this off. Oh, another unit of energy, of heat, is the kilowatt hour. We talked about this in Physics 1. 1 kilowatt hour is 3,600,000 joules. I don't know why I bring this up here, but sometimes kilowatt hour, we use that when we're talking about how much energy it costs to heat using electricity. BTUs are another common energy unit. It stands for British Thermal Units. Many furnaces are rated in BTUs per hour. Air conditioners are rated in BTUs per hour. Okay, we don't really use that here though. A BTU is basically sort of the used customary unit, like the calorie. It's the amount of energy necessary to raise the temperature of 1 pound of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit. All right. I don't have the conversion here, but anyway. Of course, we know that the joule is the SI unit for energy, and we introduced this in Physics 1. It's named after James Prescott Joule. He's the one who figured out that heat was a form of energy. He did this using a mechanical device. It would convert potential energy into heat using this system. And he noticed that an equivalent amount of potential energy would raise the temperature of water simply by putting the weight on the mechanical stirrer. The change in temperature was proportional to the energy. It clearly showed that heat was a form of energy. Benjamin Thompson had demonstrated something similarly earlier, but he wasn't able to convince everybody with his experiments. All right, let's talk about specific heat. Specific heat is a very important physical quantity for materials, okay? What it is a ratio of how much heat must be added to a substance for a given amount of mass and change in temperature, okay? So basically, if we're following SI units, the specific heat will be the number of joules divided by kilograms degrees Celsius. And again, there's a delta T, so we don't have to use Kelvin. But Kelvin would work here too, okay? So the SI unit for specific heat is joules per kilogram degrees Celsius, okay? What about the CGS unit? I gotta think about even what the CGS unit for energy is. I think it's an erg. So it's like ergs per gram degrees Celsius. All right. Here are some different specific heats for many different substances. What we notice is that denser materials generally have a lower specific heat because they're just denser. They're heavier for the same volume that they occupy. So light metals like aluminum are around 900. joules per kilogram degrees Celsius, or degree Kelvin if you like. Iron is much denser, so much more dense, so about twice the specific heat. And then even heavier materials, copper, brass, silver is very dense. Look at mercury, lead. As the metal gets denser, generally the specific heat gets smaller and smaller. Okay. What's impressive though is just how much specific heat water has. Look at that, 4,186 joules per kilogram degrees Celsius. Okay, tremendous amount. In fact, what's strange is steam has about half the specific heat. So does ice. So liquid water is sort of this special, very high specific heat material. And that's important because in the summertime, the ocean takes a lot of energy to heat up. So if you go down near the ocean, generally the temperatures are going to be much more moderate during the summertime. It'll be hotter inland, but cooler near the ocean. Why? Because the land's very easy to heat up. Okay? Only a little bit of the heat penetrates far into the surface. So generally what you're doing is you're heating the surface of the land up, very, very small thickness, and it's the air that gets very hot above it. Water, not so much. High specific heat means that even on the hottest day, this water is absorbing a lot of heat, keeping the temperatures moderate. Now, in the wintertime, when it gets very cold out, we get the reverse process. Here, the oceans give up their heat, making the winter times probably a little bit foggy or foggier, but a little more moderate than they would be inland. You ever watch the weather? And they predict all the snow. Well, the further you are inland, the more likely you're going to get snow. That's exactly what happened during the last storm. Near the coast, because the water generally keeps the air warm, you don't get the amount of snow that you get inland. This also leads to a constant breeze. Okay? During the summertime, where the ground gets very warm, the air rises due to its lower density and flows out over the ocean. The ocean air cools the air, causing it to become more dense and sink. And then it gets pulled in because that warm air was heated and rose and was pulled away. This creates a convection cell. Okay? So during the daytime in the summer, we generally get an onshore breeze as long as there's no prevailing westerly wind. The opposite happens during the nighttime. The land cools down faster than the ocean, causing the air to sink over the land. It's pulled over the ocean, which has now become warmer than the air, causing it to rise and expand. And the onshore breeze reverses to become an offshore breeze. So the shoreline can actually generate its own weather, even where the weather pattern over most of the country can be quite stagnant. That's why everybody loves to go down to the shore during the summertime. And again, okay. Sorry, I've forgotten this. SI units for specific heat, joules per kilogram degrees Celsius. Metric units, we can use calories per gram degrees Celsius. So you don't have to use ergs. Again, looking at the equation, here's our equation for heat. If there's no phase change taking place, the heat added to a substance is equal to the product of the substance mass times the specific heat times the change in temperature. Okay? Obviously, the more mass that we have, the more heat we have to add in order to get a large temperature change. The larger the specific heat, also the more heat that has to be added to affect a certain temperature change. Okay. Let's take a look at something. A steering strut near a ship's furnace is 2 meters long, with a mass of 1.57 kilograms. Has a cross-section of 1 times 10 to the -4 meters squared, and during operation of a furnace, the strut absorbs a net thermal energy of 2.5 times 10 to the 5th joules. Find the change in temperature of the strut, find the change in length of the strut if it expands freely, and if the strut is unable to expand, what is the internal stress developed in the strut due to the thermal energy? Okay, let's do the first thing first. We are given the amount of heat, right? It absorbs 2.5 times 10 to the 5th joules. We are also given the amount of mass, 1.57 kilograms. We can look up the specific heat of steel, okay, and use the specific heat to find the change in temperature. So we're going to solve for delta T here. Okay, let's divide both sides by MC. This cancels out with this cancels out with this. We're left with delta T is equal to Q over MC. Okay. Here again is how much heat is added from the furnace. Here's the original mass of the strut. Here is the specific heat of steel. So what we see is the strut gets really, really hot, 355 degrees Celsius. Okay. How much does it change its length? Okay. Well, we're going to assume that, I make the assumption that it starts at 0 degrees. That's fine. We'll do this anyway. We're going to assume that the change in temperature is 355 degrees Celsius because they don't give us a temperature to start out. So I'm going to start at 0. Probably should have started at 20, but I'll start at 0. Well, here's the linear thermal expansion for steel. Here's the original length. Multiply that by 355. And it changes only about 7.8 millimeters. Okay? Not all that much. All right, how do you find the internal stress? We got to use an equation that we probably talked about very, very briefly. Okay? It's that force over the area, the amount of stress is equal to Young's modulus times the change in length divided by the original length. Okay? Basically what this is it compares stress to strain. The Young's modulus is the gives us a ratio, it gives us the proportionality between the two. Again, so you'd have to look at some previous chapters to come up with this. All right? So we're asking, what is the stress? Here's the stress, force divided by area. It's going to be in pascals. The Young's modulus for steel is 2.0 times 10 to the 11. That should not have been, it should be 1 over. In any case, the units are wrong here. That is actually pascals. I don't know why I put those units there. But in any case, here's our change in length. Here's our original length. And if it's not allowed to expand, that will generate 7.8 times 10 to the 8 pascals of stress. Okay? So that's a much earlier idea. But this incorporates two ideas from the chapter. Linear thermal expansion from earlier in this chapter, and specific heat. Now, this is what we're going to spend a lot of time with. It is the calorimeter, okay? The calorimeter is basically something that is insulated, so heat can't make its way in, okay? Heat can't come in, and heat can't come out, all right? Basically, with the calorimeter, we are very careful to keep it insulated. Here you can see there's actually a, oh, it just changed on me. There's this insulating material. Actually, this is a gasket they're going to use to create a space. But we try to keep as little thermal energy entering in as possible. And we can introduce any thermal energy that we want in a controlled fashion. In this case, they're going to introduce it electrically. Okay. Whole idea here is we want to see how much heat we need to add to a substance of some given mass to affect some temperature change and calculate the specific heat from that. Okay? The whole idea is, in most situations, the total change in thermal energy, the total heat that flows from one substance to another, is going to be 0. Okay? Generally, we drop a hot metal into a bath of cold water. The water gains heat, the metal loses heat. So there's a net 0 gain, okay, for the entire system. And as long as we keep the heat from the outside out, we can use the final temperature to find out specific heat. Now, the way I like to do these problems is this. I like to do them in a nice organized table. You can use a table if you like my idea, or you can completely ignore this if you don't like it. It works well because it keeps everything organized. I have a tough time keeping everything straight in my mind, but we can see it's set up very much like our heat, our specific heat equation. You've got Q here, you've got Q equals M, here's C, and here's delta T, where delta T is the final temperature minus the initial temperature. It just keeps everything organized. By seeing what's happening with one substance and comparing it to another one, we can oftentimes find an unknown. Maybe Q is unknown. Maybe the mass is unknown. Maybe the specific heat is unknown. Maybe the temperature is unknown. All right. Here's an example of using a calorimeter. We have a 125 gram block of an unknown substance with a temperature of 90 degrees Celsius, so it's like a hot metal. It's placed in a styrofoam cup. There's your calorimeter, cheap style, containing 0.326 kilograms of water at 20 degrees. The system reaches equilibrium at 22.4 degrees. What is the specific heat of the unknown substance? Okay. All right. What don't we know here? Well, we don't know the specific heat of this metal. We can look at the specific heat of water, that's fine, 4186. We also don't know how much heat will flow from this unknown substance to the water. So I'm going to set myself up, set my table up This will be substance A. This will be substance B. And I say that the total change in heat has to be equal to 0. So QW plus QS is going to be 0. Set your table up. Okay, here's what it looks like. Remember, I didn't know the Q's. I didn't know the specific heat. But I know everything else, right? Okay. So what I'm going to do now is I'm going to say, let me start with the water. The initial temperature of the water was 20 degrees. At the end of the experiment, it reached equilibrium at 22.4 degrees Celsius, and that was the temperature of the substance too. So it gained 2.4 degrees Celsius, and that was my delta T. Okay? Now, Q equals mc delta T. My heat right here is going to be my mass, specific times the specific heat of water, 4186, times the change in temperature. Okay? So I just multiply mc delta T. And there we go, 3,275 joules. Well, hey, that gives me an idea. If that's what the water gained in energy, the unknown must have lost the same amount. So negative 3,275 joules was lost by the metal. Okay. Now I can solve for this. I can solve for the unknown because we know Q equals mc delta T. We have the heat lost by the metal. We have the change in temperature of the metal. It's right here. We don't know the specific heat, but we have the mass of the metal. Okay. Just solve for C. C equals Q divided by mc delta T. So I'll plug this in here. I will, oops, duh. Nice circular. Okay. C equals Q over m delta T. Sorry about that, folks. Plug that in there. Plug that in there. We have a negative over a negative, so the negatives will give me a positive. And I solve for that, and there it is. Okay? So there's the right equation. Plug in my numbers. I get 388 joules per kilogram degrees Celsius. Okay? So very simple calorimeter problem. This was simple because I only had two different things. In more complex problems, you could have multiple things, but you just go through it the same way that you did here. Let's try another one now with 3. I have water, I have a beaker, and I have aluminum that I'm going to put in there. All right? This time, I don't know the final temperature. So there's my mystery right there. Okay? If I don't know the final temperature, I also don't know the change in temperature. All right, what can I do with this? I have the initial temperature of my water, the initial temperature of my beaker, and the initial temperature of the aluminum. Okay. I have all the specific heats. I have all the masses. All right. How am I going to do this? Well, I know that the heat that the water gives off, the heat that the aluminum gives off, is going to be absorbed by the beaker. All right, let's put this all together, see how far we can get with this. The first thing I can do is try to solve for a final temperature here, okay? I don't know the heat from the water. I don't know the heat from the aluminum. I don't know the heat from the glass beaker, but I know they're going to all add up to be equal to 0. So what I can do here is put them all in the equation and set them equal to 0. So I'll take all the masses, bop, bop, bop. Here's mass of water, mass of aluminum, mass of the glass. Take each individual specific heat. It's different for each substance. Okay. Plug in the initial temperature for each. T water initial, T aluminum initial, T glass initial. And now I can solve for all my terms that have TF in them. There's a little algebra game here, right? It's going to rewrite this whole equation. It's set equal to 0 and solve for TF. Look at this. This huge equation, okay? I will take, bear with me, folks, just a little algebra. I'll take all the terms with TF in them. Notice they're multiplied by mass times specific heat. So that's all my TF terms. I'll take all my non-TF terms, put them on the other side. Okay. Divide both sides by this right here. So I'm going to move that underneath this. See, it's sitting right there. And then the rest is just putting in numbers. Okay. Here's the numerator, here's the denominator, and I get that the final temperature is 37.9 degrees Celsius. Again, a little more complex, but everything's going to have the same final temperature. All the heats are going to add up to be equal to 0. And I can use that to find any of my unknowns.